Well, we've looked at tables for addition modulo n and multiplication modulo n, so a plus b mod n and a times b mod n. Now we're going to be looking at tables for a to the power b mod n, and we're going to be particularly interested in the case where n is a prime. So let's begin with an example. I'm going to look here at powers a to the b modulo 7, and down here we have a, and across here we have b. And for example, if I take 2 to the power 3, that's 8, modulo 7, that's going to be 1. And if I take 3 to the power 3, that's 27, modulo 7, it's because 3 7s are 21, it's going to give me 6. Now, some of the rows here are not particularly interesting. First of all, if I raise 0 to any power, I'll get 0. That row is usually omitted. In fact, all the entries in green are normally omitted for reasons I'm going to explain. Because exponentiation, a to the power b, is just repeated multiplication, it's a multiplied by a b times, then by the usual modular rule for multiplication, and because we're working mod 7, the rows will repeat themselves every 7th row. So the 0th row will be the same as the 7th row. The row 1 will be the same as row 8, and row 2 will be the same as row 9. Because, for example, if I look at 2 raised to the power 3, then modulo 7, that's going to be the same as 9 raised to the power 3, modulo 7. It's not going to be true, however, that if I increase b by 7, I'll get the same result. And we can look here. We have 1 down to 6, and if we increase by 6, now this is the interesting thing, we have the same, if we go from 1 to 7, we're increasing by 6, then we get the column is repeated, but not if we go from 1 to 8. We see that the columns are different. So we'll come back to this in a minute. So far we've seen that this row here and then these rows here, because they're just repeats of previous rows, can be deleted because they don't really have any particularly interesting new information. And we also observe, and this is the interesting point, is that we have this column here of 1s. This red column of 1s is very important, and we will prove the appropriate theorem called Fermat's little theorem about this in a little while. This is not to be confused with Fermat's theorem, which was actually only proved in the 1990s and was much more difficult result. So now, because we have, we'll just accept that we have 1, we can compute, of course, in particular cases, 2 to the 6 is 64, and 7 9s are 63, hence the remainder is 1 after dividing by 7. I take another example, 4 to the power 6, that's going to be 2 to the power 12, that's 1024, 2048, 4096, and if you divide by 7, the remainder should be 1. And now we see that if we look at, say, the column corresponding power 7, now a to the 7 is a to the 6 times a, and this is equivalent to, this is congruent to a because a to the 6 is congruent to 1. These entries are all congruent to 1, or they are 1. A raised to the power 8, that's a to the 6 times a squared. A to the 6 again is congruent to 1, so a to the 8 is congruent to a squared. Similarly, a to the power 9 is congruent to a cubed, and a to the power 10 is congruent to a to the 4th, which is telling us that this column down here is the same as this. This column down here is the same as the column 8. The column down here of 3 is the same as the column 9. Column down here corresponding to 4 is the same as column 10, and so on. And for this reason, we can omit these columns. In other words, all the columns after column 6.